It lasted only a second. A sudden flash on the edge of Jupiter's disk. Bright, sharp, gone. But it was real. Multiple observers saw it. Cameras were already rolling. And within hours, astronomers confirmed what we had just witnessed live. Something slammed into Jupiter. And we caught it. Jupiter is no stranger to impacts. In fact, it's the solar system's heavyweight defender. With more than twice the mass of all the other planets combined, the Jupiter exerts an enormous gravitational pull. That gravity acts like a cosmic vacuum, attracting asteroids and comets that might otherwise wander inward toward Earth. So when something hits Jupiter, it's not shocking. What's shocking is catching it in real time. The recent flash was detected by amateur and professional astronomers alike, a testament to how far observational technology has come. High frame rate planetary cameras, once reserved for major observatories, are now common among skilled skywatchers. And many of them routinely monitor Jupiter precisely because impacts, while brief, are not rare. This one stood out. The flash appeared near Jupiter's equatorial region, glowing intensely for about 1 to 2 seconds. It was bright enough to be visible in multiple wavelengths. Observers immediately began comparing footage, checking timestamps, and ruling out camera glitches or satellite reflections. The confirmation came quickly. This wasn't noise. This was an impact event. Jupiter's history with impacts is dramatic. The most famous occurred in 1994 when fragments of Comet Shoemaker-Levy 9 collided with the planet over several days. The explosions were so massive they left dark scars larger than Earth itself, visible even through modest telescopes. That event changed planetary science forever. It proved that major impacts are not ancient history. They're ongoing processes. And Jupiter, due to its immense gravity, experiences them more frequently than any other planet. Most impacts, however, are much smaller, likely caused by objects only a few meters across, essentially cosmic boulders. When they strike Jupiter's thick atmosphere at tens of kilometers per second,
You've most definitely heard of Jupiter's Great Red Spot, the gigantic storm that's been raging for...
the energy release creates a brief, bright flash. No crater, no lasting scar, just light. Based on brightness estimates from the recent event, scientists believe the object was likely between 5 and 15 meters in diameter. That might sound small, but at impact velocities exceeding 60 kilometers per second, even a modest asteroid carries enormous kinetic energy. To put it into perspective, an object just 10 meters wide can release energy comparable to several thousand tons of TNT when moving at those speeds. On Earth, a similar object caused the 2013 Chelyabinsk airburst over Russia, which shattered windows and injured over 1,000 people. On Jupiter, it barely leaves a mark. That's because Jupiter's atmosphere is immense. Thick layers of hydrogen and helium absorb and disperse the impact energy quickly. Instead of striking solid ground, most small objects vaporize high in the atmosphere. But every observed impact tells us something important. First, it helps refine estimates of how many small objects exist in the outer solar system. Asteroid population models depend on real collision data. Jupiter acts like a detector, revealing how often debris crosses its path. Second, it gives insight into atmospheric dynamics. The brightness, duration, and decay of the flash helps scientists model how energy propagates through Jupiter's cloud layers. And third, it reminds us that the solar system is not static. It's active, violent, unpredictable. Interestingly, many of these impact flashes are first detected by amateur astronomers. Programs like DETECT, short for Detection of Transient Events on Jupiter, allow observers worldwide to upload footage for automated analysis. Algorithms scan thousands.
Jupiter is a massive, terrifying planet.
Unlike large comet impacts, small asteroid strikes usually don't leave visible debris trails. After the recent flash, follow-up observations from both ground-based telescopes and orbiting observatories searched for dark spots or atmospheric disturbances. So far, none have been confirmed. That suggests the object disintegrated high in the atmosphere. Jupiter's massive gravity accelerates incoming objects dramatically. By the time they enter the upper atmosphere, they're moving faster than most solar system bodies ever experienced near Earth. The energy scales quickly with velocity. That's why even small objects create brilliant flashes. Events like this also highlight Jupiter's role as a planetary shield. Many astronomers believe Jupiter's gravity reduces the number of comets and asteroids that reach the inner solar system. By capturing or deflecting them, Jupiter may have indirectly contributed to Earth's long-term habitability. However, that shielding effect is complex. Some simulations suggest Jupiter can also redirect objects inward under certain conditions. Either way, its gravitational dominance is undeniable, and every impact we observe adds to the data. The last confirmed visible impact before this one occurred just a few years ago. In fact, several flashes have been recorded over the past decade. Most last less than 2 seconds. Some are detected in visible light, others in infrared, but each time, the reaction is the same. A moment of disbelief, then verification, then excitement, because witnessing a planetary collision in real time is rare. It's a reminder that even giant worlds are not immune to cosmic chaos. There's something almost cinematic about it.
It lords over the solar system.
A tiny speck of rock, wandering silently through space for millions of years, suddenly encounters the largest planet in the solar system. In a fraction of a second, it converts its motion into light and heat, briefly outshining entire cloud bands. Then it's gone. No trace, except for the data. In the footage, scientists are now analyzing the light curve, how the brightness rose and fell during the flash. That profile can reveal clues about the object's size, composition, and entry angle. A sharp spike followed by rapid decay suggests a compact, dense object. A longer glow might indicate fragmentation during entry. Early analysis suggests a fast, single-body disintegration, which means it likely wasn't a loosely bound comet fragment, more likely a small asteroid. This also helps calibrate impact rates.
July of 1994, scientists around the world watched in amazement as the comet Shoemaker.
By comparing how often we detect flashes with how often we're observing Jupiter, researchers can estimate how many such collisions happen annually. The answer? Probably dozens. We just don't catch most of them. That's changing. With more observers monitoring Jupiter continuously, detection rates are increasing. Some astronomers speculate that within the next decade, real-time planetary impact alerts could become routine. Imagine getting a notification that something just struck another planet. That future isn't far away. For now, though, we have this moment. A flash in the clouds of Jupiter. Captured live. Verified within hours. Analyzed across continents. It's easy to think of the solar system as calm, planets orbiting.
It turns out that the most common planets within these inner regions are not rocky at all. How did our solar system evolve in such a different direction?
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.